Welcome back to Physics with Miyoshi. I'm here with my sled, getting all ready for winter. It's a little bit early, but I want to demonstrate a little bit about, well, not demonstrate, do a little mathematics and physics about what it takes, how far a sled would go when the only force acting on it is, the only force acting on it to impede its progress is kinetic friction. So, let's find out. So we have our sledder here. Notice my beautiful picture. And the only forces acting on it are, of course, our weight of the sledder and normal force, and the kinetic friction going the opposite direction of its travel. Notice there are no other forces. We're not constantly propelling it by a jetpack or anything like that. We just have the force of friction slowing it down. Well, the question is, how far is that sledder going to go if its initial velocity was 4 meters per second in the, in this case, the left direction, right direction. Okay? And we wanted to go find out how long it takes to get all the way stopped, so we know our final velocity is 0 in that case. In this particular case, it doesn't really matter what the mass is going to be. We'll find out during the mathematics that the mass would cancel out. So let's find out how far this person would go at 4 meters per second, and knowing that the kinetic friction between the sled and the icy or snowy or whatever surface that is 0.0500. Okay, so we know that the sledder is not accelerating the vertical direction, so we know that the sum of the forces in my y direction is 0. So the only two things acting on there are the force of weight, or the weight, which is my mass times my gravity, and the normal force acting up from the ground up toward the person, up to the person. So we can do our sum of forces, our Newton's second law, and we know that the normal force minus the force of weight is 0. So that normal force is then going to be the force of weight, which is my mass times my gravity, or the acceleration due to gravity, to be more technically correct. Then we can remember our frictional force, and just like with our static force, our kinetic force, friction force, is equal to our coefficient of kinetic friction times our normal force. The negative sign here is to show that force is going the opposite, the direction of our motion. And that then the mu k, or the normal force, or the coefficient of friction, kinetic friction, times our normal force is just negative mu k times mass times our acceleration due to gravity. If we look at that equation a little bit differently, if we say that our force of kinetic friction is equal to our mass times acceleration, then we can show, then that's also the mass times our mu k times g. Then we can show our masses, and we divide both sides by the mass. We know that their acceleration is negative mu k times g, or our coefficient of kinetic friction times our acceleration due to gravity. Again, the negative sign just shows that it's going left in this case, or it's opposing our motion. Alright? Now, once we find that, we remember, as long as we assume that we have constant acceleration, we can then find our V average. Our V average is our initial plus our final divided by 2. So we know that our average velocity is 2 meters per second. Add the 4 plus 0, divide that by 2, we get 2. And then we remember from our kinematic equations that the acceleration is just our change in velocity divided by time. And we can rearrange that equation to find our time is our change in velocity divided by acceleration. So we have 0, because that's our final velocity. We have 4, that's our initial velocity, 4 meters per second. And then we divide that by this acceleration, negative mu kg. Notice there's a negative sign on top, because this will be a negative 4. Divide that by a negative sign on the bottom, we end up getting a positive 8.16 seconds. So when we divide our 4 by our 0.05 and 9.8 meters per second squared, our units also will bear out the fact that that is in seconds. Okay, then again, going back to our kinematic equations, we have distance as our average velocity times time. We just plug in those numbers for our v average, which again is 2 meters per second. Our time is 8.16, which we just found here. And then we know that that ends up being, or multiply that together, we find out the distance that person would travel, that sledder would travel, would be 16.33 meters. And that's that. Now, you can also find it with just a simple equation. Once we find our acceleration, we can use this other kinematic equation. Vf squared is equal to vi squared plus 2ax. Again, I usually don't use this equation. It never comes to my brain. But it is a perfectly legitimate formula to use. And we rearrange it so that our 2ax is negative vi squared because we know our vf squared is 0. Then we rearrange that, and x is negative vi squared over a 2a. Plug those numbers in, again our negatives cancel out, and we end up getting that same answer, 16.33 meters, which we should of course expect because we know that initial equation, this equation here, came from these other equations and doing some substitutions mathematically. So, a little about kinetic friction and how that affects a moving object. In this case, we found our distance that a sliding object, in this case a sledder, would have on a particular surface that has a particular kinetic friction coefficient, and starting with a specific speed. So, a little bit again about kinematics comes in again with our Newton's second law and knowing just a little bit more about friction. So, hopefully this helps with the mathematics of it all and explains a little bit about the friction. And thanks for tuning in, and we'll talk more about more of Newton's cool things he talked about in his laws, and more about forces, and next time on More Physics with Miyoshi. So thanks for tuning in. We'll see you next time.